So, hello, I'm Alexis Bourget. I work for HarfangLab. We're a security firm, sorry. And today I will present how we migrated from Python to Rust, or HDR agent. I will explain what an HDR is. And I will explain what an HDR is, what it does, so you have an idea of the constraints we have, and why we were porting our agent, because it was working and we had a product, so why risk the port? And I will go into some technical details and some very technical details on bugs we had. First, what is an HDR? What are we porting? And what are the functionalities we are interested in keeping and some losing, notably the bugs? And the constraints, because just before they talked about speed and memory, and we have pretty much the same. So another is sorry for that, a security product to watch over a fleet of computers. Computers here can be a server, a mobile, a VM, an endpoint like my computer. We don't care. There is a console to control them all, like the One Ring. A backend to store everything, which is basically a giant database, and up to 100,000 agents on each machine or more. And the highest I have seen is like 200,000, so it needs a lot of data. And specifically, I will talk about the agent, the thing that is installed on each endpoint. And an agent has a few core functionalities. First, telemetry. We need to see everything on the machine, on the endpoint. It can be processes, network connection, file access, logs, file correction, reading. We need to detect if those are malicious from rules written by humans, by analysts. And we need to respond. After that, if, for example, you deem Firefox to be a virus, we need to kill it. Once we have done that as a base, here is how an HDR works, so you have a little idea of how much work goes into this for the performance constraints. So we have rules written by humans that are security analysts, and they know their stuff better than me at least. And they know that Firefox is a virus and Chrome is not, in their case. They have events that come from the OS, so it can be, for example, if you're using Linux, you can watch a process with eBPF, and all that goes into the engines. Here I put a few names, Sigma, Yara, they're all common engines among HDR's firms. So once we have studied an event, we can decide to allow or block it and report it if necessary. And all that, imagine launching an app on your computer and it takes 40 seconds each time. You wouldn't accept that. It's horrible. So we have a lot of constraints on an agent. As a security product, most customers don't want to see it, don't want to pay for it too, but that's another problem. So we must be invisible when not blocking a virus. And that implies not interfering with normal operations. So most of you are probably developers. On each compilation, an HDR will watch each file accessed. That's horrible for performance if we are too slow. Like a few milliseconds can be horrible when it's on a few thousand files. So we need to be lightweight too, to not be a source of lags, and most of the time we try for a response time of a few dozen milliseconds, at least for processes. For files we try to be much faster because it's very visible. And it means everything must happen on the endpoint. We can't offload calculation on the backend, which means we have constraints on the memory too, for example, when reading all the files. And as a security product, we must be reliable. So the figure, the 500k event per minute is something I saw last Thursday, so it's a real one. Even under that, an idea ODR was taking 50% of the CPU, not 100, which is a nice win for us. And a crash is a potential security breach, which is not a common case, I think. And it makes it interesting when porting and interacting with C APIs. So why are we porting? We had an agent and it was working. And I will talk a little bit about the non-argument for Rust, the things that were not arguments in our case, but are interesting for Rust in general. And the arguments we had for Rust and the objectives of the port, so you can have an idea when I talk about the results, about what we did and why. So there was once a Python agent, and it was averaging about 3% CPU and a few hundred megas of RAM, and that works, but that's average. Under 500k events per minute, it's the machine is dead. Like you can't do anything. And it was designed in a startup, and not that we make profits now. And it was hard to maintain, hard to extend, and a pain because the language wasn't helping us a lot. It was relatively slow, like we were limited in some new features by Python itself and by the speed we could achieve even with C bindings, notably because of the global interpreter lock in Python, which is a big lock limiting Python to a single thread. It's annoying to package Python for a lot of platforms, especially macOS, where signing is important. And if you have ever tried to write a Windows service in Rust, it's even more annoying, especially when our concern as a security product is watching everything. It means coming up very, very quickly in the boot process, and Python is no good for that at all. So we had to write a binary in C++ acting as a true service, and the number of bugs with that is way too high. So first, a little talk about the non-arguments for Rust. One often cited argument for Rust is memory safety, and it's true, Rust is memory safe, there is no problem with that, but it was not a problem for us. Python is memory safe too, so we didn't have any issues with that, or at least not more than in Rust when interacting with C. And as you see, it's about the same number of line of codes. It's pseudocode, so of course I cheat a little here, but it can work at about the same. And there are a lot of other non-arguments. Thread safety. Python has one thread because of the GIL, so no problem here. And Rust has the send and sync traits, which mark which data types are safe to share and use across threads. So both have them, non-arguments for us. CFFI, we do a lot of CFFI to interact with OS APIs, like Windows, macOS, Linux, pretty much all the time. And it's not a problem in other cases too. It's simpler in Rust because it's integrated in the language, but it can work in Python. And available packages, it was a non-argument, but in the other direction, it was better in Python, mostly because, as you saw earlier, Crates.io is 10 years old, and they have to keep up with like 25 years of Python, something like that. I wasn't born. And so there are about four times the number of packages in Python, and that's only counting the source and the package index. And thankfully, the community was not an argument because both are nice and active. And for example, contributing to open source in both is very, very easy, and they're very welcoming. So it's nice when fixing bugs. But now that I have the non-arguments, what are the arguments in favor of Rust? So multi-threading, because Python is thread safe, but it's not really multi-threaded. And Rust is, there is no limitation on that. And the control, a part of speed is controlling how much you allocate the size of your structures at this speed. And Python doesn't offer that, and we had troubles with that in some cases, especially around structures on networks. Maintainability, so I talked about it a little earlier, but Python is hard to extend in big projects, and we had around 60,000 lines of Pythons at the end. So maintaining that becomes hard. And Rust is statically typed, both are strongly typed. So we had no problems with that, and we have now much more lines of Rust and no trouble still. Speed is important too. I named a few dozen milliseconds as our target, and Python, like Go, as a garbage collector, and it was interfering sometimes a lot, especially under load, which is a time when we want speed. And Rust has no runtime, no GC, and so no problem. Distributing Rust is also much easier, especially since we basically statically link everything. So it's a single binary, you drop it on the platform it is for, and it works, mostly. And as a security product, you have a few other concerns. One is hardening, which is important because if our agent is like non-buggy, but the library beside it is our agent is buggy and we have a breach. Again, statically linking everything is important and works well as a workaround. And finally, I will talk more in details about this later, but obfuscation, which means hiding items in the binary, like you write a binary which prints hello world and you hide the hello world, can be done in Rust. It's hard to impossible in Python at best. And now that we have chosen Rust, what do we want to do with the port? So we want to improve the design. We want to maintain backward compatibility because we were offering, and we are, it's offering the data we upload to the backend to our client, and it's their data, really. So they can do whatever they want with it, and if we break compatibility, they won't be happy. We won't be happy either. We wanted more control to be able to deploy new features that would use more CPU or more RAM, for example. We wanted to improve security with obfuscation and hardening. And we wanted to prepare for new platform. I talked about how packaging Python for macOS is annoying. It's pretty much impossible when you're a security product that need to access the macOS framework. So I will talk in details about maintaining backward compatibility, about the bugs we had, and we had a lot of them. We are not perfect. So notably the bane of everyone, time zones. A memory leak in Rust that wouldn't have happened in Python, because it's interesting, and specifically about something in our product which is called the Sigma engine, and an example of where porting from and having two languages working together can be a problem sometimes. The improvement to security we made and the results. So maintaining backward compatibility, we started with end-to-end tests, a lot of them. Oh, I'm going so fast, sorry. And keeping the same data format, sometimes we had troubles with Rust crates. As they were available, they work very well. The object crate allows reading any kind of binary, Maco for macOS, PE for Windows, ELF for Linux, but it doesn't yield the same format as the PE file library in Python, and that was very problematic in some cases because we were dependent on that format accidentally, but now we have terabytes of data with that format. We need to be compatible with it. So there is this comment in our code, which makes me sad each time I see it, but there is a big file which is a port of some part of the PE file library, and we had, as part of the port to Rust, to keep that behavior and keep it now indefinitely. A certain form of bug compatibility proved necessary, and it's no fun. There are two comments about that, at least I found. On the left for you, there is sometimes the wrong behavior was coded in Python, and we had to keep that in Rust when we saw it, so that again the data was exactly the same. End-to-end tests here are a lot of help. And on the right, it was not a breaking one, but an annoying one. The versions formats in Rust and Python beyond app, point B, point C are not exactly the same, and you can break Python with that. You can literally make the versioning library crash all the time because it doesn't support some formats that are supported in Rust. And so we had to work around that a lot. I'm gonna now talk about the bugs a little more. So upgrading from a Python agent, so I installed in a way to a Rust agent that was just a single binary, broke a few times, and that's something to think about when you deploy on client machines and not on servers, because you don't control them. They deploy as they want, when they want, and sometimes the network breaks during the update, and now you don't know what you have on the end machine. The regex syntax is not the same, and there are a lot of regex in the rules I talked about. And it's very, very annoying when some obscure regex is not working anymore. And obviously it's a breach too, because you have a rule that cannot be applied. We use gRPC to communicate between the backend and the agent, and a problem we encountered is that the Python gRPC implementation is slow at runtime. And we had to do a lot of workaround, often called more server, and throw more server at it to make it work. And as I said with the regex syntax, the parity in detection was not exactly the same. So we didn't see any real bug or breach linked to that. But during the transition period, we were very stressed about that, because if our old agent would have detected it, but the new one wouldn't, that's like a big leak in our product. And catching all that is impossible, because that will mean knowing about all the viruses in advance. So I talked about time zone. I'm gonna expand on it. Here is how you can get a date from a timestamp in Python. And there are a few bugs with that on each line. So first I get a timestamp, and then I try to obtain the UTC timestamp from it, the UTC date from it. And the first case from timestamp has no argument. It's a bug we encountered. You use that, you think, okay, it works. But if you look at the line below, there is no timestamp, time zone information, and especially it's not UTC. There is an UTC from timestamp that seems to be the solution. That was the first review. It worked, but because there is no time zone information in it, and you only discover that when someone quits the current time zone and go into another, and you see the movement being much more than expected, like a customer going from France to Germany, for example. And finally, you need to use from timestamp with another time zone and another argument, and that's not obvious in any way anywhere, especially with the name of the previous function. It's something we encountered a few times, and we had to ban literally the UTC from timestamp method, so at least we are now aware about it and we have silence about it. But and I talked especially about that because I said we use protobuf, and protobuf doesn't include time zone information in its object, because it saves a byte simply, and when you have 500k event per minute, a byte each time is a lot. So it means that when using protobuf from Python, you have to be very, very careful with time zones. And for us, a timestamp is important because, for example, it could be someone authenticating on the machine, and we need to know when. Because if a process was launched before or after, it may make sense or not. Here, I dunked on Python, but Rust is not perfect too. On the Rust side, it's very, very easy to be beaten too. Not with protobuf. Here, the APIs are done pretty well. But with the OS APIs, so I took the example of Windows, it's the same on the other systems. The system times object can bite you because it has no time zone information, again, like protobuf. And the functions that return it sometimes don't say what they return. Like you have to experiment and say, okay, it seems to be UTC or not. And some of them document it wrong too, which is fun. I talked about a memory leak to show that Rust is not perfect. It's a memory leak from the start of the month. I'm sorry for the graph, it's a little small. So it's we interested in the orange bar. It's going up and it's going up and it's going up again. And it was because we were listing users on a machine with 3,000 users, I think. I don't remember the exact count. But each time we were losing 15 megabytes of memory. And each time it was slowing down the machine a lot. And it's on the domain controller. And here it's a small company. If you do it at like THALES with 50,000 people, I don't want to see the jump, literally. It was a bug in the Rust wrappers, and it wouldn't have happened, and it didn't happen in Python because of the garbage collector that was saving us all the time, and we didn't see the bug there. If you're interested, there is a pull request where we fix the bug, and I can show it to you again at the end if you want a photo. And it was a two-line bug, like a very small two-line bug with a wrongly used object. But this is the sort of thing that can happen in Rust that we missed in Python because the garbage collector was saving us, and we encountered it a few times. So the port was not without troubles. Most of the time we didn't, thankfully. And here it's in a third-party library, so it wasn't even code we wrote us. It was code that had been used for years by other people, but I suppose they didn't have 3,000 users to list each time, so they didn't see it. Or it was not a long-running program too, I don't know. And a bug that is less linked to Python and Rust and more to having two distinct implementation. Rules, when uploaded by a client, are validated first in the backend, so they know immediately if the rule is valid or not and if it can be used. And after that, they're sent to each agent, which will, if the rule is for the OS citizen, use it and compile it. And now, to fix the bug, we have the same Rust engine everywhere. But don't worry, if you have never seen a Sigma rule, it's not very, very complicated. But what's important is the event ID here, which means we are looking at a library load. And it means there is a set of fields that is valid or not. And there is no obvious error. It's YAML, it looks ugly because it's YAML. But it's looking for a danger.dll. Okay. But command line is not a valid field, and our backend was not checking that. Our agents were, and so the client was uploading a rule that was he was told the rule is valid, and all the agents in Rust, so as the upgrade progressed, were refusing it, which means that the rule that was previously working was now not, and they didn't even know about it. We had a lot of troubles with that because we can't upgrade everything all at once. You can't migrate 1,000 and 100,000 machines at once. And so we had to check all the rules if they allowed us to check for errors, make aliases and everything. And it was annoying. And that was simply due to having two competing implementations, both coded by us. We were completely aware of the code for both. But that can be one problem of ports, having differing implementation for a time. Finally, a little more, a better result, a positive result, improving security. So we added a lot of obfuscation with strings, reference to statics, and algorithms. And just after that, I will show examples. And a lot of hardening in our agents to prevent DLL hijacking and to prevent crashes, because if you ever see another in Rust, I will show you a technique code to make it crash that they probably missed, because we experienced it a little. So obfuscation, what is it? First, you take, here it's Rust code, but you can take C, C++, whatever compiled language you want. And you want to hide the string hello world. You don't want it to be visible in the final binary, because here hello world is not a bridge, obviously, but when it's an API endpoint, when it's a name of a table in an SQL database, anything that can be used to reverse engineer your binary can be a trouble. And so without obfuscation, the code is very, very easy to read. Here it's assembly for macOS, so if you only know Intel, sorry. And at this address, L and name 2, there is a string hello world in clear, and then you just look where it is used, and you can reverse engineer half the binary instantly. And we're very sad. With obfuscation, you add just a little macro, 2 lines more here, and you can do shorter. And it becomes this. And you want to cry each time you reverse the thing, because you can look at the base data. There is nothing. And this is not free. There is a cost at runtime for this that can slow down your binary. It was one reason we wanted Rust, because it freed us the performance for this. So we regularly check this isn't impacting performance too much, and in some places we can remove it, but we try best to not remove it. So this obfuscation still has one problem. It is reversible. You take the assembly, you find the constant, and you find the value used at runtime, and you can find the string. You can find it in the RAM too, for the binary, and for us it is a concern, because for example the ANSI that was talked about earlier, when doing a qualification, will try this, and they succeeded in Python. I think they abandoned on the Rust binary. They never told us anything. So we wanted sometime non-reversible obfuscation, and here you can do a compile time hashing of the values you want to compare, and it's even more. It costs even more in terms of performance. Here I use SHA-256 in my example because I was testing performance, but you can use SHA-1, SHA-512, any hashing algorithm you care about. But it will have a cost in terms of space, of binary size. Obfuscation for us is like 5% of our binary size, and it's a lot. Here at runtime, do something is never in the binary. You will never see it anywhere. You will simply see hashing in a place that has no business having hashing, and it hides a lot too because of that. You can also do it for environment variables. When looking at debug vars, here debug var again is never in the runtime binary, and so you can hide a lot of things what you are looking at, for example, that way. And so, for example, here I was using it in a test too to see if I could reverse the debug var somewhere, and see that it was used, and use it to activate logging in the binary, so that if someone couldn't do it for this, they couldn't do it for us too. Now we have obfuscated agents, but obfuscation is a bonus. Like, we try your best to do it, but it's not necessary if we can't. Hardening, on the other hand, is absolutely necessary, and hardening comes in two forms: preventing crashes, as I said, and preventing DLL hijacking. The second can be relatively easily prevented via static linking, but there is still a problem. You're on Windows and you want to interface with kernel 32.dll to have the standard APIs of Windows, and you can't static link it. Any update of Windows will break it. There is no stable interface for Windows in terms of this call. So you need to control DLL loading, and that can be done relatively easily in Rust. In Python, it can be done too, but it's done later, and so half the Python library have already loaded, and boom, you have a breach. And I talked about crashing under the air in Rust. In Rust, there is std_vars functions, which lists environment variable as UTF-8. If it's not UTF-8, it panics. End of the game. Now your ADR must restart. You have a 3-second breach, and the machine, the attacker is an admin. Oops. And it's very, very easy to do. There are lots of libraries using it. And so, on the still left for you, you can clean up environment variables, and also I added a little line about banning some vars and removing them. That way, they cannot be used to attack you. Because, for example, in Rust, there is a variable called rust_log, which is often used to activate logging for libraries. And it's hard to obfuscate which libraries you are using in a binary in Rust. And so, for example, if you're using a request hyper to connect to an HTTP something, they will see it and they can just look at the code there, see that it uses logs and activate it and see everything you do in terms of logging for free. So you need to block that in some way, and you need to block it very, very soon. This is not enough. You need to also remove it from the C environment that is underneath the Rust environment, which is a pain. And on the right, I'm showing how to control library loading, because the set default DLL directories is simply a function to control where you load. But to load it, you need to have to call it. You need to have kernel 32. So you have the chicken and the egg problem, which comes first. And there are ways in Rust to do that. We didn't find any in Python. So another win for Rust here. And now we look at the result. First, in time, the port took us 2 years. The Python agent was developed in total over 3.5 years, 2 of which overlapped with this, because we couldn't just stop delivering something. So it's not free, it's not doable. It was a big product with important security concerns, but we couldn't do it in like 2 months. We had to rewrite a lot of things, and after that, the macOS MVP support, which was one of the things we wanted to do, was achieved in just 4 months, which is much, much better than 2 years. And it hasn't broken down in any way until now. And the average CPU and RAM are way, way down. So we got from 250 megabytes to like 75 on average. And CPU diminished by like 5 times 5. And we are usually around 0.2 to 0.5% on a like slow machine. And bigger machines even less, because we take the same operations. And it wasn't easy for us, because 2 years is a lot of uncertainty when your company is like less whole than that at first. But we ended up with like 170k lines of Rust against 60k lines of Python. Most of that is accolades at the end. You can remove like 50k lines of Rust for just accolades because formatting. But even in your result, that's still twice the amount of Rust as in Python. And that's partly because, as I said, there are a lot more packages on the Python index than on CreateMario that are geared toward pretty much anything. If you paid attention, I named ML machine learning engines as one of the engines we can use to watch events. And anything machine learning in Python is like import a library, do 5 lines, and you have it. Machine learning in Rust is not that. We had to re-implement a lot of things, notably compression, image parsing. And on the other hand, we have a lot more code, but it's much, much more stable. The Rust agent has been in production for 9 to 10 months now, and we never saw a big crash. We saw a lot of load under some workload. We saw bugs, but we never saw crashes or blue screen. The Python agent blue screened some 500 people company, and more sometimes. And we're very happy. We didn't deliver it to some clients with 100,000 machines, because I don't think they would have been happy. And we had the performance improvement we wanted. I showed the figure just before, and that allowed us to add like 2 or 3 engine or sub-engines that way, and a whole new machine learning model. So we have now several machine learning model in the agent, and it's still 0.5% of CPU on average, and only 70 mega of RAMs. Do you have any questions now? Sure. Écran qui marche.
Thank you for your presentation, very complete. I have one question. So from what you said, I understand that you rewrote it completely from scratch, and that you weighted feature parity based mainly on your end-to-end tests to ensure both were working the same. Did you consider other ways to bring Rust into your Python code? For example, by only porting some kind of Python into Rust, making an assembly with that, and eating the Python code base?
So we considered it, but we had two problems with that. First, the design was, like I said, the Python agent was not very extensible, and I will stay polite, but a pain to work on. And so we wanted a clean start too, using what we learned with the Python agent, but not like interfacing with it.
More questions? So I have a question myself. You mentioned machine learning for Python, that is really easy because a lot of things are done. Have you seen some trends in machine learning libraries for Rust?
We haven't watched for them, I think, now. Mostly because we are not developing the machine learning algorithm in Rust. We are developing them in Python, and just the resulting model is just read and used in Rust, but the training is not, and that's the part that moves a lot.
Okay. More questions? No? Okay, thank you very much.